Okay, now that the sun has moved on a little bit and may occasionally flash in my eyes, we're going to look at vibrational electronic spectroscopy. So, if you manage to wrap your head around how we can do vibrations and rotations at the same time, this is largely the same principle. So, you can probably imagine that if we have an electronic transition, there might be a vibration to go along with it, and we'll get a fine structure. But there are a few more complicated things in this. So let's go and recap them. So what we need to know is that there are electronic transitions that happen. So this is where you are physically changing the electronic state of your molecule. You're taking electrons from their ground state orbitals, the bonding orbitals maybe, and promoting them into anti-bonding orbitals or other more complicated ones that are on higher energy. And that takes a lot of work. That takes a lot of energy. So we're now out from the microwave region to the infrared region into the visible and the UV region of the electromagnetic spectrum. And you probably will pick up from atomic spectroscopy that can be quite complicated. There are a lot of things going on in electronic states that determine what the spectrum looks like. If your spins are all aligned, it will be one energy level. If some of them are against each other, it will be a different level. There are loads of different terms and states, and it's a very complicated topic just on its own. And we're also going to now include vibrational spectroscopy in it, so you should know that one. The molecules are vibrating back and forward. We're going to stick to just the diatomic case and look at what the electronic spectra of these diatomic molecules could be. So you know all things about potential wells. And where we're going, well, vibrational fine structure appears in electronic spectra. So normally you probably don't see this a lot because when you deal with UV spectra in the lab, you're used to seeing these really broad peaks. But mostly that's, again, a side effect of being in a solution. If you put anything in a solution or a liquid phase, there are a lot of interactions that smear the energies out and actually make things very, very complicated, and we can't really resolve it properly on a spectra. So everything actually spectroscopically broadens rather than stays fine. But if you took UV in the gas phase, you would see fine structure. And if you remember back to basic atomic atomic structure, you may be familiar with things like the Rydberg equation and solar spectra, and how we managed to prove that orbitals exist within atoms by looking at solar spectra, usually with little spectra that look like this, because the lines are fine, but there are more than we might expect. There's a lot of complicated things going on. And then we're going to go into what is the Frank-Condon principle, which is just a name given to the general idea of overlap, which is the selection rule that we're going to be talking about. Because there aren't any hard and fast selection rules here, unfortunately, so we're going to have to go through it. So, electronic spectra are complicated. So why are there more transitions? Well, this is going to be fairly straightforward, right? We've got an electronic state here, ground state. We're going to label it 0. Doesn't matter whether this is an orbital or a collection of orbitals. It's just the electronic state of the molecule. And then we're going to promote it to a higher one. So we've taken an electron, it's absorbed some UV light, and it shoots up higher in energy to a different orbital. The electronic configuration of the molecule has completely changed. But that molecule will also have vibrational levels in it. Now, those do not have the same progression as rotational levels. Remember, in the anharmonic oscillator, they do eventually converge onto the limit. So if you actually promoted something into this state, it would actually dissociate, it would break. I'll redo this diagram in the second part of this lecture and show you what that can be represented as. And here we've got the same sort of progression. So of course we can have, usually in the ground state, we could in principle go up to here, land in the ground state again, or we could come up and land in another state. or in fact many other states. The selection was not as straightforward as in vibrational rotational spectroscopy. And you will also have to remember that we don't really populate this. These are vibrational levels. So that is V is equal to 0, that is V equals 1. We don't have many molecules in this level. This is not very well populated. That level is quite empty, at room temperature at least. So molecules going up to here and landing somewhere else don't get seen very often. These transitions are sometimes called hot bands because the molecule would have to be kind of physically hot. There goes the sun again. To actually start here. So we'll ignore them. We'll just look at this and we'll look at why they land at different levels at the top now. So we can get more than one transition appearing in the electronic spectrum. So if we were to do it in the gas phase, we would get multiple lines, which is what we see in some things. So let's have a look. There aren't hard and fast selection rules here. So what is the overlap and what's the Frank contact principle? For that, I'm going to have to redraw our potential wells again. So let's have a look here. I'm going to draw one down at the bottom because I'm going to draw another one at the top in a moment. And this is, let's just say it's going to be just a diatomic molecule. We've got one atom vibrating against another one, so we've only got one coordinate. This is our potential energy, and we have a Morse potential or similar that comes down, up, and then levels off. Remember, this being the dissociation limit. If you can give the molecule that much energy, it breaks. You've given it enough energy to overcome this potential energy barrier here, and the atoms become free. And we have energy levels within that. They begin to bunch up. We hit a continuum and a limit, and so on. Now that Morse potential there doesn't come from nowhere. It's there's an equation for it, but there are parameters associated with it that are properties of the molecule, and those properties are all electronic. So if you want to squeeze atoms together, it's the electrons that are going to do the repelling. A little bit of the nuclear charge as well, but mostly the electrons. They are going to have a bit of pressure to stop them from being overcompressed. If you try to pull them apart, again, it's the electrons that are going to hold those molecules together. Molecules stay together because of electrons and electronic structure. So if we change the electronic structure, I'm going to draw a new potential up here. This potential could in fact look completely different. We could have the same coordinate, same potential energy. So these should be capital V's for potential energy, shouldn't it? And maybe the equilibrium bond length has changed. Maybe the dissociation limit has changed. Maybe it could be some other shape. So it could be actually further out here. Our equilibrium bond length could land here. It could be a wider potential well. It could have a lower dissociation limit. A higher one even. We still get all those bunchings. So what you can see, we've got an equilibrium bond length here and one here as well. So this then, well, we maybe come back to this after the quantum mechanics course, but there is a wave function associated with each of these vibrational levels. We can kind of solve the Schrödinger equation and figure out what these vibrational states look like. And maybe one will be like that, one will be like that, one is like that, and so on. Same up here. These just wiggle back and forward as waves, but the number of times they wiggle back and forward is going to be very different. And then what happens is this middle point here is the most likely place the atoms will be. It is where the wave function is maximized. Again, if these terms don't necessarily make any sense, come back to it after the quantum course. We'll have time to revisit this. Right here in the middle, and if we project this up, what you can find is that line does not land on this exact same point here. So that says that this transition from, let's call that b equals 0 to v equals 0 is actually very unlikely to happen. It's not going to happen. We're not going to see that transition on a spectrum, or at least if it is, it's going to be very tiny. Let's keep going up. What we do land on is v equals 2, right here. There's actually a considerable bit of overlap there. Maybe a bit more even at v equals 4 if I was to scribble that on as well, but I'm running out of space on this diagram. So what you can see here is that, well, there's a couple of things going on. One, this is actually a general version of what we mean by selection rule. What we're looking at is an overlap between states. If we have one state and another state, do they overlap? Do their quantum mechanical descriptions have a lot of overlap? We'll do overlap more thoroughly in both quantum mechanics courses. If the overlap is good, the transition happens. If the overlap is poor, the transition is at least less likely to happen. And that's the general idea behind selection rules. So that's the Frank-Condon principle. If the overlap between them is really good, we see the transition. And that is why basically the electronics fine structure is usually different, and it will depend entirely on what electronic transition you're looking at and what the molecule is. It's not very easily predictable in advance, but the electronic spectra can give you that information. Anyway, this is just kind of a qualitative introduction to it. We're not going to do this in a lot of detail. All the maths and the really applicable stuff is all in the rotation and vibrational stuff. This is just almost for final information to round everything off. But we'll show you a few more examples in the advanced information section.